Okay, so this next module takes us to what we call higher cognition. I put a little symbol up here of the sort of stuff we'll be doing, like using conceptual phrases to point at objects in the scene, like perceptual grounding. That would be something that we'll consider cognition, higher cognition, a little later. Usually there's a day has passed, so I'm not going to revise all that. What I want to remind you of is in these interfaces, we just talked about sensory interface and the motor interface, and it's through those interfaces that the peaks in the fields get meaning, and I can skip that. And let me take this slide here perhaps to make that point. And so you could, in a way, in the fields, the peaks are the units of representation. The peaks is an instance of something, right? The something is like a category. Here, for instance, we might have a neural representation of movement, visual movement. So if a dot moves in a particular direction, we can represent neurally that percept. And so the notion in the field is it's represented by a peak of activation in an appropriate parameter space, for instance, a space spanned by the horizontal position and maybe the vertical position and the movement direction, 3 dimensions. I only plotted 2 dimensions here for convenience. So this would be movement direction. And then I could have an activation field where positive activation means I see movement of that kind, and subthreshold activation means I don't. So a peak of activation would reflect that percept that you see movement. So this would be a unit of representation of an instance of a category which is moving objects, and you would represent by that peak. In fact, I've done a lot of work on movement perception, and I can say from that work that we can actually do both behavioral and neural method measures on the width of that peak, and we can really establish how wide that peak is. You do that, for instance, in experiments where you look at motion inertia, so where you change the display from cycle to cycle, and at some point you offer two. It's like in apparent motion where it's discrete, like a TV set, right, where you have different images, discrete images, and they create apparent motion in your perception. And you can create a possibility where there, in one frame, they put 2 possible targets that your object could move to, and then you tend to prefer the one that's closer in movement direction to the movement you already had. And you, in a sense, you can sort of check how much activation is transferred in time to that next movement. So there's a whole lecture to explain that in more detail, but this is real. There is some neural reality to these peaks. And very similarly, in the motor system, I actually showed you that concretely yesterday, that in the space of movement parameters, you can think of a peak as representing one particular intended movement. I showed you how you can directly record that from neural populations. And I also hinted how in behavioral experiments, you can get some sense for how, over which range, for instance, from this time movement initiation paradigm, where you see how spread the responses are in multiple trials and how they gradually shift as you get more information. So that's a very fundamental way of how we look at these things, which isn't trivial in the sense that it is actually what is called localist neural representations. It's this notion of a space code that every neuron or every actually activation variable votes for a particular value of in some space, a location in a space. So it's not actually the distributed representations that many of you will be familiar with that are, for instance, used in deep neural networks and a lot of connections networks. And I'll explain that in more detail later. I think it's maybe tomorrow in the last lecture, I will be talking about that. And so this fact that these peaks are units of representation and use this localist representation, that's quite important to us, and you already saw that it comes from that, which you studied in the exercise, from this fact that we have a very simple hypothesis about neural interaction, about the connectivity patterns within populations that generates these states. And these are these local excitation, global inhibition kind of interaction patterns, and they have this feature that they don't need to know exactly what pattern you represent, they can just represent any peak, but it's always a peak. It's always local, but anywhere in the field. So that's a principle that I'll be using now when I talk about higher cognition. So we're coming from this perspective, and we'll have to compare how that compares to other perspectives. So when you have this perspective going to multiple dimensions, it's not a problem per se. So we've used one-dimensional fields in most examples so far just for convenience, because it's simple to do, but there's mathematically nothing very special. You can do this in 2D, you can do it in 3D, in 4D. There's a problem if you do it in very high dimensional spaces with the numerical realization, because it's going to be very costly then, and that actually is reflected by the fact it's also costly for the nervous system to have that many units. And I'll be talking about that in a little while. There are some subtleties about that that mathematicians like to work on. Like there are other solutions, high dimensions. You can have like ring solutions and so on. This is more or less exotic stuff. So in practice, it's really no real difference. I'll come to, but there are new functions that will arise as we increase dimensions. That is what I will be talking about. I want to first mention that there is this one thing that we kind of fold into that we talk about zero-dimensional fields, which are really nodes, discrete nodes, right? And it's a little bit loose talk to talk about them as zero-dimensional fields, because what we actually do is that we often have these nodes and as ensembles, a whole set of nodes. For instance, often they're all competing with each other. Like in the examples you'll see, we'll have nodes for color concepts like blue, green, red, yellow, and then only one of them can be activated at a time. And that's more like a quantization of an underlying field, a discretization of an underlying field. And so, for instance, you can think of the readout level of a lot of deep neural networks like that. They use localist representations at readout, because then you make a decision for one category versus another. And the nodes represent these different categories. So the nodes are more like a discretization of low-dimensional maps, sometimes, for instance, as vector quantization in self-organized feature maps. And we use sometimes more complex coupling structure than just that they all compete, and you'll see that. So that's the thing that's a little bit cheating to call that zero dimension, because there's more to it. Okay, so that's just scaling itself. But now I want to talk about higher dimension functions that arise when you have more dimensions. And of course, they're interesting primarily when it's different kinds of dimensions that you have, not just X, Y, Z of space, but when their different dimensions are combined. And I'll talk about binding, about search, and about coordinate transforms in that spirit. So first, let's think about what these dimensions are. So in the examples, we didn't really elaborate there very much, but certainly there are spatial dimensions. Like the visual space is actually two-dimensional. Auditory space is also two-dimensional. We have a very good sense of elevation and some kind of orientation to compute in different ways, binaural difference for horizontal, and there is some subtle anisotropy of the transform function for each ear that gives us some sense of elevation. The third dimension is actually more of a feature, like we have a sense of depth from many different depth cues. The binaural difference is actually used for stereo cue is used for just for, disparity maps, so just one estimate of depth. So you can think of the third dimension as a feature dimension over these two spaces, just like you have other visual features like local orientation, motion, texture, color, scale, size of things, and so on. And of course, auditory features like pitches and formants and so on. And that's actually just empirical observation that two-dimensional space is very important, and you will see that plays an important role in our theory, because we'll be assuming that there is some kind of canvas, two-dimensional canvas, that is not actually necessarily tied exactly to your eyes or your head. It's actually sort of anchored in the world that organizes how you deal with objects. We'll come to that. There are more features, there's also a whole body scheme, right? You have some surfaces. That's a subtle thing of how well we know about it. It's probably also much about hand effectors in space where they are in outer space, not so much on our body. So if you take a funny body configuration, you actually have a harder time tracking where things are. There are motor features. I showed you movement direction. There's something like the direction of force against which you act and things like that. It's a whole topic to talk about. And I'll show you examples of more abstract cognitive features. There's something like order, ordinal position, we call that. So order in a sequence. That's a kind of a dimension. So when I'm talking about combining different dimensions, I'm combining different things like that. So for instance, visual space and a visual feature like color over space. That's the example I will be using in a lot of the work here. So in the nervous system, these different kinds of dimensions are always tied to each other, or very commonly tied to each other. So even the classical Hubel and Wiesel tuning curve reflects that, right? I assume everyone knows that old story, so that if you, let's say, record from primary visual cortex, that you have receptive fields, that is certain regions on the retina, this dashed line here, where contrast or luminance patterns that you project there will drive a neuron, so will make it spike. Here's a spike, some recording of spike from a neuron. So only neurons, only stimuli that fall within that region. But then their spiking also depends on other feature dimensions, like here the direction of movement, which is covariant here with the orientation of a line element. So that only for certain orientations, like here, the ones this is centered on, the neuron fires, and for other orientations, it fires much less. So that is 3 dimensions, right? It is the orientation and the 2-dimensional visual space, the receptive field, which itself, receptive field is just a spatial outline, but it also has a receptive field profile where the neuron will fire more when you project something in the center of the receptive field and less when it's at the boundaries of the receptive field. So this could be viewed already as some kind of binding, in the sense that a particular combination of visual space and orientation is represented by those neurons. We call that anatomical binding, in the sense that you have, say 1 neuron for every combination. I have neurons that represent all kinds of receptive fields, so represent in a topographic way, represent visual space. And you have orientation tuning, let's say, and any combination is there, and they actually need to, because you have the cortex is layered, it's only 2-dimensional, you actually need to reorganize that. So to put different patches next to each other, there's a whole industry of figuring out how that works, how there are certain spots where the continuity of neighborhoods, the so-called topographic property, is broken to put the next patch there of what is really a 3-dimensional space. And very similar ideas apply to many other feature dimensions you're aware of. Movement is like that, and texture is really spatial frequency is like that, and a lot of other things. And in a lot of those, receptive fields play a role. That is, everything also depends on visual space. And that's actually true even if you go relatively far from the sensory surface. The receptive fields become very large as you go higher, further away, but they're still there. There's still some spatial sensitivity, and you'll see that makes some sense. So in our thinking, that would be captured by high-dimensional fields. I'm plotting again just 2-dimensional for convenience, but 3-dimensional is sort of the minimum for anything visual. So I'm taking always just 1 spatial dimension for simplicity, and then 1 feature dimension. So this, for instance, would be a representation of a anatomically bound or joint representation of color and visual space. Again, just 1 dimension. So if you have a 1-dimensional scene with color and location, that scene would be represented by a 2-dimensional pattern of activation, where the green object at this location makes a peak and the blue object at that location makes a peak. Right? Kind of trivial. It's the field version of that map. Now, if you have that, you can do a couple of operations on that. One of those is to extract the features that are conjointly represented. So unbind them. So for instance, if I have a pure color population that only represents color and a pure spatial population that only represents space, I can extract by summing, for instance, across the 1 dimension. I can do that with just taking the max, or take a soft max, or different ways of doing that summing, but they will lead to the same quality of result, that you extract whether or not there's any activation along space at that color value. So for instance, if you did that, you get a bimodal distribution for the two colors and a bimodal distribution for space. You can also do the reverse, that is, you can have one-dimensional representations, just like only know the hue and only know the space and combine them. So actively bind them. And you do that in this picture by creating ridge input. So this would project to all of those locations. That would be essentially if the inputs I was just talking about is bidirectional, would establish a ridge or such a ridge, and you could think that you can arrange things such that where these ridges overlap, input would be larger, and if you make sure that the detection instability occurs only at that level, you've tuned things that occurs when the two inputs overlap, you would create a peak at the intersection of these two inputs, and that's how you could put an item there by knowing these two-dimensional values. And that's assembling a bound representation. This is where the binding problem arises. It's perfectly fine if you have one object. If you have two objects and do that at the same time, you get misbindings. If you know, essentially, you don't know if the green is this left one or the green is the right one. All of those four possibilities are there. So one idea, if these kind of operations happen at all, combining lower dimensional into high dimensional, then you have to do them one at a time. And I'll provide you arguments for that and argue that it's a sequentiality bottleneck in the brain. That is actually the reason why we have that sequentiality. It's just kind of remarkable that a lot of these information processing cognitive architectures like SOAR and ACT-R have this as their central feature, this bringing an object in the foreground and some kind of computational metaphor that it corresponds to the CPU loading an item into memory. But actually, CPU can load a lot of items into memory at the same time, as long as it knows the addresses. The nervous system has a bottleneck that might come from this. Now, I'll show you that from this binding and unbinding problem. Now, search. Search is the thing that if you open an AI textbook, that will be the first chapter. It's about search and search algorithms, which none of which are physiologically reasonable. People don't do that and can't do that. And I'm not very good at it. That's why we need Google rather than do it ourselves. So what form does search take that nervous systems do? It takes the form that is best known from visual search, but that you can also do in other modalities. And that is a combination of these two processes that I just talked about. It would be a case where you have a bound representation because you really have a visual scene, let's say with two objects. And now within that, you want to attract your attention to something specific that you know something about. Like, I want the blue thing. I want to reach for the blue thing. And so what you do is you provide this ridge to the blue thing, and where it overlaps with one of those two-dimensional representations, you create a peak, and you do that again by choosing the threshold, right? So that only those locations that receive input from the sensory surface that get the boost from that ridge can build a peak. And then you can read out the location of that peak into a spatial field and can steer, for instance, eye movement to that or a reaching movement or something like that. That is the core principle of visual search. And you can see how that would generalize across many different kinds of areas. Now, this would be single-dimensional single feature search, and we'll come to more complex things in a little while. And in fact, Raul Greben will be talking about that. So I just hinted that. So this is the architecture he will be presenting. And I want to highlight just one or 2 points about that. So the generalization of that is that you would have multiple features. So for instance, color is the one I just referred to. Orientation might be a possible one. He'll be using shape in some cases through template matching, and I believe size was another one we used in another simulation. And all of those could be represented in the manner that I just talked about. So as three-dimensional fields, so one feature dimension over the two-dimensional visual space. And the interesting thing is that they all share space, right? They would all include space as a dimension. That would be very important. And in these spaces, you could do the search operation just like I hinted. Rather than put in a ridge, you have to put in a slice now into them in 3 dimensions. So for instance, if you know which shape you're looking for, along the vertical, you would find that shape and then excite all the locations that are compatible with that shape. So that's a slice of the field. And similarly for orientation and for color. Now, I explained how a single ridge or now slice could select a location where there's matching information. And the more non-trivial aspect of this in real visual search is that it might be across multiple such feature space fields that you might have to do that. That has to do with the fact that color, orientation, and shape are represented separately, not as one. I'll be talking about that a little bit, why that is the case. Empirically, that is the case, and this model is compared to psychophysical data that essentially show signatures of the postulated neural processes for that. And I'll be glossing over that. So Raul will show you this video, perhaps, I'm not sure, where actual camera, I mean, as you see, an object being brought in here will drive selection processes. The system is now attending to this transient object, and it will be looking for the partner of that object for this one. It also has a scene memory. These are cut through 3-dimensional feature space maps, and it will ultimately, here it actually recognize this object here first, but it doesn't match because it has different size, and then it actually finds the correct object here at this point. So he'll explain how some of this works, and I will explain tomorrow how these sequence steps of the different activation peaks here arise, because this is just one simulation running. It is one neural dynamics evolving in time. It's not no algorithm that says, now do this, do that, and so on. And so that's something we'll be talking about tomorrow. So that's how search arises. And I talked about the anatomical binding. I'll talk about coordinate transforms, and then I actually combine these into talking about binding through space. I wonder if I should have actually changed that order, but that's the order I have. So coordinate transforms, you will discover, are linked to that binding notion. It's sort of also some kind of bindings, kind of interesting. Now, first, let me clarify what coordinate transforms are, and I'm claiming they are very fundamental. They are fundamental, certainly to sensory motor cognition, and I will show you later, they are actually also central to a lot of higher cognition. In fact, I'm claiming that if you do inference or you do mental arithmetic, if you say 5 + 6 is 11, then you're actually doing a mental coordinate transform. That's why it's in here. So in sensory motor, it's perhaps clear that plays a role because the coordinates in which you perceive don't match necessarily the coordinates in which you act. For instance, if you're looking at this cup, it's in certain coordinates for your visual system, but your hand is anchored to your body, and so your hand needs to reach to that based on where your shoulder is, let's say, or where your body is. So, for instance, when you look somewhere else, the sensory representation changes, but the body representation doesn't change. And so that difference says that you have to establish the coordinate, from the visual coordinate frame, you have to establish the body coordinate frame so that it is invariant under that change of your sensor configuration. That's the challenge. Here is another example of that. So for instance, when you have a scene representation where you know where different objects are in the world, let's say, in a body frame, right? To compute movement parameters, you have to do a coordinate transform, because movement parameters are relative to your initial position of the hand. So for instance, movement direction, movement extent refer to your initial position of the hand. And actually there is some new evidence, which I'm not even sure is published yet, but I saw the preliminary work by a group in the US who have actually shown that the techniques I'll be showing now with coordinate transforms might be compatible with what motor cortex does. That it makes this kind of coordinate transform, this so-called gain field techniques will get to that in a moment. So I'll illustrate the idea around the classical retinal to, classically it's considered as retina to head-centered, but I'll talk about retinal to body-centered because it turns out that it's actually head and eye movements are very coupled, and so it's actually not it's more complicated to disentangle them. So here's an eye. This is from Sebastian Schneegans' chapter in the book. An eye looking at this visual scene, and so on your retina you would have that kind of image. On the retina, of course, it is flipped because it's a like a point camera, but I'm unflipping that to make it more intuitive. So you would have that visual scene represented in retinal coordinates. So the fovea would be here on the red object in the middle. And now if you're making a gaze shift, for instance, to look at that object, then obviously that object is in the fovea, and this would be then to the left of that. So the reference frame in which the sensory information arises is retinal in nature. And on the other hand, what I argue is then when you want to reach, you need to anchor it in the body, maybe even anchored in the scene. If you want to, for instance, come back to your desk and know where the cup is, then you actually might have to anchor the memory on where you perceive the desk. Maybe you're not in the same position relative to the desk, and so you can generalize that. Okay, so that's a problem that is one could think of as a transformation, a mapping that is, we call that steerable, that is flexible. Now, neural networks are very good at mappings, right? You can take a neural representation of one thing and have cables that project it onto something else. Let's say from retinal space to body space would be very easy if it is a unique mapping. But this is a mapping that is not unique because depending on where you're looking, it's a different mapping. So it's a whole family of mappings. We call that steerable. That is, there is a steering dimension, the gaze angle that says which of many possible mappings between retinal and body space is currently relevant, depending on where I'm looking. And you see the analogy to binding is that what you need to determine how to project, how to transform, is a combination of both. You need to know where you are in retinal space and where you're looking relative to the body, right? Gaze angle is relative to the body. And so that is a bound representation. So this two-dimensional field would be a bound representation where every location here combines both the retinal value and the gaze value. And if you know that, then you could uniquely determine how to project onto another field that represents things in the body frame. I'll sort of make a derivation, sort of visual illustrative derivation of what that wiring needs to be. It's approximately, and then that turns out to be correct. So the binding. So here is very natural. So, it's natural to think that you actually need to actively bind. You might have some sensory information about where your gaze is. Could be proprioception in your eye, and also some head sensory information. Could also be different copy that or reference that you would know that you made this motor command, and therefore your gaze is going to shift in this particular way. That would be presented in some neural representation of the motor system, while the visual information comes in from the retina, goes through LGN into visual cortex. So they have clearly different sources. To combine them, you need to do something special, namely to do something that is described in the field terms by these combinations of ridges or slices and ridges, and that's how that would come about. And here is sort of the formalization of that. It turns out that this field, the bound field, has properties that have been observed. I'm not sure I have a slide about that. They've been observed in parietal cortex, famous discovery of Anderson and others, called gain field. So what it turns out is that what happens here is that the receptive field that in retinal terms that neurons have then depend on the gaze angle, and they tend to be blown up or reduced by the gaze angle. And that's exactly what locations in this field have as a property. explained here in this chapter. So let's look at that. So we'll refer to this situation where we have a stimulus in the world. So it has a particular body position relative to the body at plus 10 degrees, and will vary where the stimulus is on the retina by varying the gaze direction. So currently gaze direction 0, the retinal and the body representation are identical. And here's the retinal representation, here's the gaze representation. This is the combined gaze retinal combination, and it would be corresponds to that position in the world. Now, if I shift gaze, wrong direction, shift gaze to fovealize the stimulus, then my retinal position is now 0. So this has moved to the left, is 0, and my gaze angle has increased to be 10. So this is moved up, and this is still in the same location in the world. So the peak is now here on at this position. And now let's look at another gaze angle. I turn the gaze away, so it goes to -30. And on the retina, this moves further to the right, maybe intuitive, right? So it moves to the right, and it's still at the same position relative to the body. I'm here on this position. So if you go through that again, you will find out along that diagonal, you get all the combinations of gaze angle and retinal position that correspond to a fixed position in the body frame. And if you take a different diagonal, then it will be corresponding to a different position out in the body. So the projection is to sum along these diagonals and project it onto a field that will then be the body-centered representation of that target. Of course, in reality, it doesn't have to be exactly diagonal. There could be some issues about the eyes and their exact geometry and so on. So it will be some set in more general terms. It will be just some set, but a fixed set of combinations of these conjointed representations that map onto the lower dimensional representation that you're projecting to. We typically think of these kinds of couplings as bidirectional, and that means that we can then actually do the transforms in different ways. For instance, very simply with bidirectional coupling, what you can do is you can take a retinal input, combine it with gaze to predict where it's on your body, but you can also have a memory of where something is relative to your body, or maybe, for instance, you grasp it, and then you can direct your gaze at it. You could compute the gaze angle at which the object will be foveated, or you could know your gaze angle and predict what it will look like on your retina. And that is something that we actually compare to some experiments. So first here simulation. This is a simulation where two objects are on the retina. These are the objects here on the retina. There are two peaks in the retinal representation. This is my gaze angle, and now creating the body framed body-centered representation of these two objects. And you see these shadows are the ridges. There are ridges in all directions because there's bidirectional coupling. You see here, this would be misbindings, right? But they are not as strong. You actually need a single peak along one of these two dimensions. And typically, of course, gaze is a motor thing. We only have one motor system and one state. So the gaze is always going to be monomodal, but that plays a role in other uses of coordinate transforms. Now, a moment later, these inputs are turned off. And actually, I think I was speaking wrong. The blue is the red is the prediction, and the blue is really input driven. So we turned off the stimulus. This is in memory mode. This is working memory in body frame, but there is no working memory in retinal frame. And now what we'll be looking at is but there is a prediction currently which comes already from this projection of where these objects are on the retina. And now what we'll do is we'll do a gaze shift. So you will see there's a gaze shift here. Like now, it's a cat, gaze shift, and this memory is stable. And now the intersection of this new location with a projection from this predicts a new location of these objects. Right? So I'll just show you that again so I get a sense. So you induce these, induce the memory, and now this is where they were on the retina first. And now after the gaze shift, they are in this new location. right? And this is something that is observed in experiment. This is a famous experiment going back to Goldberg's lab. This is an LIP, but there are a couple of other areas where things like that have been seen. So this is a very kind of really, I don't know, mind-boggling stuff, but it's old stuff. So for instance, here you have receptive field. So this is a monkey that is fixating here on this point. It has this particular neuron has this receptive field. So if a stimulus falls into that receptive field, this neuron fires, the stimulus is on here. If you turn the stimulus off, it keeps firing actually, so it has some kind of memory function. But if the monkey moves the fovea away from that location so that the receptive field now is no longer driven by that input, then the firing actually decreases. So it's actually making a difference on whether it's consistent with the current stimulus or not. So the stimulus remained on here all the time. And now the interesting bit is that if the monkey fixates here, it's a different cell. Monkey fixates here, so and you turn on the stimulus. You have this little stimulus. It's not in the receptive field of this neuron when the monkey fixates here, but then the monkey moves the eye to this new fixation point. This is the movement. But by the way, by the time this is done, the stimulus has already been turned off. So when the monkey fixates here and the stimulus now would fall into the receptive field of that neuron, the stimulus is no longer present, but the neuron fires. It fires only transiently because the stimulus is gone, but it fires. Interesting. And the model explains that. So I'm not explaining the details of the model, but it does that right. So that's just an illustration that these things are neuromechanistically real and concrete. A last point about the coordinate transforms. They are, of course, really higher dimensional. I took one-dimensional space and feature space, and of course, really the retinal space is two-dimensional. The gaze field is two-dimensional, right? You have two gaze dimensions. Now, Listing's law says the third one doesn't really matter, the eye rotation. And the body-centered representation is two-dimensional when you know where an object is relative to your body. And so the transformation field is four-dimensional, right? Which is already a little bit challenging. So here's a representation of 4 dimensions by a lot of two-dimensional ones arranged so that the position in the larger array is the other 2 dimensions. That is the actual nature of this model. That's important for a point I will be coming to now. So what I want to talk about now is binding the scaling. So how do you go beyond these simple high-dimensional representations? This is the picture with the binding like that. That would be maybe consistent with other people's thought of high-dimensional vectors representing complex stuff, like in deep networks. But that's not very flexible. And I'll now talk about how to get something more flexible. And we'll see how far we get through all of this. So by the end of this, I'm ready to just do 2 examples and I'm done. I'm not sure I get through everything today. So I'll show you how this simple form of binding does not scale and then propose an alternative binding through space. So let's just think for a moment. If we were to take this higher dimensional field idea seriously, what would happen? I took the numbers here just so that we get 16, which is an upper limit of how many neurons there are in the brain, 10 to the power of 16. So it's a little bit just made up, but you can easily make this argument. So we certainly know that neurons in the visual system, let's say visual cortex and first couple of areas, they represent retinal dimensions. They represent depth in the sense of disparity, orientation, color, texture, movement direction. There's some scaling, size, and there might be multiple like that. So if I count it correctly, these together would be 8 dimensions. If you need about 100 neurons per dimension, now could discuss whether it's 100 or it's a little less, then that would take 10 to the power of 16 neurons, right? To have the, and some, all the combinations represented by different neurons. that's more than the entire brain. So clearly that scales very badly. So it's clear that only small subsets of such feature dimensions can be bound in this anatomical way, meaning that neurons are there for every combination of the different feature values. Now, you can play a little bit with this number to get a little lower, but not easy. So a different idea is needed. There's an idea that goes back to the 70s, perhaps even the 60s, I think. And Treisman, who recently died, unfortunately, was, I think, the inventor of the idea, together with some others. I don't know exact history of these ideas. It wasn't really an idea that came from neural thinking. It came more from information processing thinking. And the idea was that you may have separate representations, but they all share a dimension which was proposed to be space. And the idea came from the fact that objects are a particular location. So if an object is of a certain size, certain orientation, certain color, it's all going to be at the same place. And that is how you know it's about the same object. And these psychophysics experiments that were done were with small little objects that were very localized. So that made a lot of sense. And so the idea would be that you know the relationship by knowing that shared dimension, that dimension through space. In the original version of feature integration theory, it was actually formulated algorithmically. It's so kind of very interesting. They were talking about a object file, and you would take the space as an address, and then you put the stuff into a file and sort of combine it. And this still, some of you might know that something called idiomotor, event coding is a theory for the motor domain of that nature. It's also driven by an idea like that. You would have a file for every action, and then you would store all the values in that. I think this would be like a memory and an address, and the address with the spatial location. But what we do is really do a neural version of that. And I'm interested in some of those ideas. This is from Raoul's architecture, but it shows up in many other architectures as well. And so, for instance, if you have these different representations like size, orientation, color, then one way of how you could select an object is by selecting a spatial location, and boosts every feature representation along that spatial dimension. So this would be a column, a cylinder in the sense of activation. So only activations in 3D that overlap with that would have a chance to be activated. You could read out the value of that by projecting out into a one-dimensional field, and then you could reassemble that somewhere else, for instance, in memory, for instance, in a different coordinate frame, by putting slices into these fields and putting a new cylinder here. It's at the same location, but it could be at a location that is coordinate transformed into a new location, and then you build the bound representation. So that will be one way of how binding could be used. And we're using that concretely in this architecture to build a scene memory. Yeah, I could say more about that. I don't know how much Raoul will say. Here's a sort of intuitive example of what that amounts to. Let's say you have these funny colored letters and you have some representation of color, and I'm just sort of saying this kind of a toy example where you would have some shape representation. So different shapes for different letters and different locations along those fields. And so let's say you're supposed to tell people what letter is the green, has green color. And the answer is going to be S, right? And so what you have is a neural representation that's driven by these two feature dimensions, in which you know where each letter is, and you know which color it has. That will be that pattern of 5 entries, and you know which shape, shape you have, it will be that pattern of activity. And so what you would do is the Q is a search task, right? It's not necessarily a visual search, it would be some kind of cognitive search where you would know it's the green, so you put a ridge into that and bring up only that peak that overlaps with that ridge that will be green. You read out where it is in space. That would make a peak here in the spatial field, and now you're making that spatial ridge bring that into this field, that brings up the peak that is spatially overlapping. So that's from the same object, which reads out, project out into the shape field, and the answer is S. You read what the feature is, the shape feature that's stored at this location. In the simulation, you actually see this ridge because all the connections are bidirectional. So there's also a ridge shaping along that form. Now, that would be a concrete way that binding could happen. Now, the experiments that Ian Treisman and others did to actually establish these kind of bindings are about change detection in working memory, and they're quite complex. I'm not going to explain them fully. They are in the 8th chapter of the book. I just want to sort of give you a flavor of that. So for instance, this would be an example where, again, using just a one spatial dimension and color and orientation as two feature dimensions. So this would be a visual scene, and you could see a visual scene consists of, red, green, and blue objects that is oriented, in these funny ways here. So this pattern together describes that visual scene. And so this would be a pattern in two fields which are here just two-dimensional, and they share the spatial dimension. And so what's shown here is how you get that into memory, working memory, which you can then use to detect any change in the scene when you show the scene again and something has changed. And the chapter reviews how the change detection part works. Now, in this theory, we can't put all of those into the working memory at once, because then we get misbindings. Now, remember that problem. So what we would actually do is select attentionally one of those objects, like in space, and that would give a boost to that spatial location, and that would make that only peaks at that location are suprathreshold enough to activate fields. These are different variants of a field only over orientation or only over color, and they provide input here, a rich input to that assembly field where we built the representation of individual objects. To bring up the peak in a particular location, we also bring in space. That same space here is brought in here. So in the actual nervous system, this would be in a different coordinate frame, would be the space maybe in your scene representation, table centered, while this would be on your retina. And that's how you can do the coordinates in this form. And then you have a copy of that field that is sustained. So this would be selective, and this would be multi-peak, and you could bring in working memory. Now you can do that for the next object, where you select this one and put that here, and the third object. So in the end, you would have this original representation in your working memory in a new spatial frame. You see the possibility for misbindings here, which we selected the right one because we did it one at a time. And so now you would be able to do change detection on that, even if your visual scene, if you do it for a new visual scene where the objects have, for instance, changed location or other things. Maybe I won't say more about that. So that is so when you do binding through space, then that is really an origin, a sequential bottleneck, because now these objects not being all in the same field, you really have to make sure that you only attend to one object at a time. I wonder if I have a slide like that. There is, sorry, I can skip that. There is so the spatial dimension can be replaced. It doesn't have to be always space. You could have something like an index, we call that sometimes label, where you say there's something shared across all these systems because they pertain to the same object given the same label. I'm not sure if Daniel Sabanes will be referring to that. We're using that in our current thinking for some of these properties. Good. So if you combine that, so think about the dimensionality. Now combine the insight that we have these separate fields with a coordinate transform, then you recognize perhaps that this binding through space really alleviates the problem of the coordinate transform. Because if you had the coordinate transform really as a neural, it really means a neural machine, right? You have an activation pattern that's in retinal coordinates, and now you need to remember where the blue thing is on the table. in some other coordinate frame. What you would have to have the cables, from all these different feature fields to all the different, same features now over a different spatial dimension, and having that means having all the different a huge dimensional space, because if without any additional thought, it wouldn't be enough to have the fourth spatial dimension. You would also have the other axes all attached to this four-dimensional space. But with it binding through space, it is enough to just transform space. And then you can look up what the feature values were there at that spatial location. And if you have that new spatial location, you can then put the feature values again into the new locations. See how that dramatically simplifies that problem. So that's sort of the line of how, out of visual cognition, you can infer about fundamental processing bottlenecks in the brain. And these actually apply across different modalities. They apply to actions as well. They have a similar idea that any action you do has different parameter values, what object it's oriented at, how fast, how long, whatever. And sort of the place of objects is different actions, and you have to have a representation for that, and very similar kind of idea applies. Good. So I'm running late. We have perhaps used a little bit more time initially, so I think I wonder how much of this I should do. Make a decision here. Let me think about that for a second. So I think I'll do this learning thing and then stop here. So I skipped this because we'll be talking about that tomorrow. I want to add this last point because it plays a role in a couple of projects. How learning comes into this. Now, learning, I assume that you're all familiar with Hebbian learning, right? So we're not talking about things like backpropagation and machine learning techniques that are very artificial. We're thinking about neural processes, and neural processes, of course, are all synaptic adaptations that occur as activation unfolds. So Hebbian learning is the natural way to think about it, and Hebbian learning works just as well, of course, within neural dynamic field theory. Dynamic field theory is a subset of connectionism. It's not alternative. You could say this connectionism is a bit fuzzy and vague about dynamical ideas, but it does include the recurrent networks. It just doesn't always do the math right, but that's sort of a technicality. So we can certainly use Hebbian learning. We typically do that in continuous time, which is also not revolutionary. So you have a time scale on which connectivities between fields over dimensions x and y evolve. So this tau would be much slower, and it would be typically modulated by something. We'll get examples that I think Jan will be talking about how the learning rates are modulated, for instance, only when reward happens do you actually learn. And then the form of Hebbian learning means that you essentially have an attractor for the weights, this minus W maximum attractor, and that attractor will be dictated by the degree of co-firing, co-variation. So population 2 defined over that other dimension, population 1 over that first dimension. When they both active at the same time, actually this F is again a sigmoid function, then this weight will be driven to an attractor in that form. So there are multiple versions of that, but you can see that works very generically. And Julia Zanimiska has in some of her projects, she did a project on autonomous learning, has realized these kind of projections. This is important in a lot of the later work, especially for nodes and fields, because nodes get their meaning in our representations through their connectivity to fields. I hinted at in deep networks, the nodes are sort of the last stage where the classification takes place. You have as a complex distributed representation, you learn the connection weight to the nodes, and that gives the meaning. And so for us, it would be typically connectivity patterns that are localized. So we'll have a node that covers a certain region of the field, and these connectivities can easily be generated from Hebbian learning. Now, the fields have a simpler form of learning, the memory trace, and that plays an important role in dynamic field theory. And I want to illustrate why we can get so much mileage out of the memory trace. And I referred to that a little bit yesterday in the example when I talked about the pre-shape, the pre-activation that may arise. So formally, the memory trace is written in our methods as in slightly different form. It's we think of it as sort of like a second thing, like a distribution. It's also an activation variable. It's not really a field. It's a bit unclear what physiologically it would be. A copy of the field over the same dimension, and it is driven by the field. So when there's suprathreshold activation, it drives up the memory trace, and when there's a memory trace, that in turn excites the field. Side note, for those who know, there can be fields that are inhibitory in the sense that they project onto something else as inhibitory variables. And in that case, a memory trace in an inhibitory field is like learning inhibition. And that's what, for instance, shows up in habituation. So this is the mathematical form we often use. So if this is a field that I have, then it gets input from a memory trace, and that memory trace has a dynamics on the slower time scale. Where, this makes the time scale here that is just driven by the suprathreshold activation in the field. And we have the special rule that the field does not evolve unless there is some activation in the field. So if there is no activation in the field, so the entire integral over the field, over the suprathreshold field is 0, then the memory trace does not evolve. And that's consistent with a lot of empirical data that we model that way. Now, this is not, so memory tracing thus doesn't represent the input. The Hebbian learning represents the input-output correlation. And the memory trace just represents the decisions, the outcomes. It doesn't represent the causes of these outcomes. So for instance, if you have a time course of stimulation that leads to these activation patterns, sometimes here, sometimes there, the memory trace represents the activation history, and it has some kind of interference, because we're assuming, there is no update of the memory trace if there is no activation at all in the field. So it doesn't forget. But there is competitive forgetting, because if there is one location which drives the memory trace, then at all other locations there will be 0 here. And if there's 0, there's decay. It will be decaying to 0, right? So there is a more realistic to have an equation where there are 2 different time scales, one for growth and one for decay. And we use that often. It's formulas in the book. There's empirical evidence that these have different time scales, with forgetting taking longer than building up. But the effect is that, for instance, a memory trace built at these locations will tend to decay when a memory trace somewhere else is being built. And that has the effect, which I don't have that slide here, has the effect that the memory trace builds something like a prior. So this equation that question was mentioned previously, we showed that even in the old Erlenhagen paper in 2002, that if you have probabilistic occurrence of certain stimuli that you detect, that then the memory trace reflects the probability with some low-pass filtering, that is the recent probability density of these different decisions. So for instance, if you have probable and not so probable choice, the memory trace represents that probability of the choices. So it can be built as a process model of how priors come about. So the memory trace is something like a first order Hebbian. Right? Hebbian is a second order, it's correlational, and the memory trace is sort of like non-correlational, first order. It just looks whether there is suprathreshold activation. And there is a mechanism for that known. All connections networks actually have a bias input. There's one input that just essentially determines the resting level of those neurons. Most connections don't talk about dynamical terms. They don't call it resting level, but it's called bias unit. And the bias unit plays a role in some of the learning rules that you might be familiar with. And it simply happens so that in dynamical field theory, that bias unit does a lot of work. In neural networks, it doesn't do so much work because typical connected networks have a lot of inputs, and then there's only one bias unit. You can imagine if you have 100 inputs and one that votes is the bias unit, it's a very small influence, mostly used for some kind of homeostasis. But in the neural fields, as I demonstrated in my simulations you discovered yourself, the peak generation can amplify small differences. So what the bias unit can do is create small differences, and you can bring up peaks from that small difference in a way that is not explained by different input strings, because if you bring up a peak from memory, from scratch, without any current input, then the difference in input connectivity doesn't actually do anything for you. So it's much more important to keep track of that. So we haven't invented something new. We're just elaborating on something that was used somewhat in a somewhat minor role in a lot of connected neural networks. Now, there are different proposals out in the experimental literature for what mechanisms there might be for such memorization, and tell you there are many different ones. It's very difficult to study because of the very small, graded influence of that. So we can't really say that for sure, but it's not excluded from by physiology. So the memory chase will be important in a lot of what we will be doing later on. So I will be using the memory chase, and a lot of our projects use it. So I had to review it here. I did this a little bit without enough embedding, perhaps. I want to close here because these two examples that I now have for how we can use the elements of binding through space and coordinates forms for higher cognition. I think I don't have the time to do that. I'll just add it on tomorrow, and you will then get special lectures on a lot of those. We will have a special lecture on perceptual grounding of relational concepts by Daniel, on visual search by Raul Grieben, and then actually on Thursday we will have John Spencer give a presentation about a huge integrated model that uses all of those techniques, including the memory trace. So I'll